Hello everyone. Welcome to the series of lectures on the course Calculus and Numerical Methods. In this video, I will be continuing with the properties of convergent sequence that I started in the last lecture. So in the last lecture, we proved three important properties of convergent sequence. So let me start with the fourth property. So that's a continuation of the previous chapter. This says that's number 4. Supposing I have a sequence xn of real numbers, let xn be any sequence of real numbers such that xn converges to a point x where the limit to which it converges is a positive point. Alright, I have a convergent sequence xn which converges to a positive real number, that is x. Okay, so let me geometrically just draw this in. Let's see what we are expecting in the result. So supposing this is my, I'll just draw it again. Supposing this is my real line and I have the 0 is here, and all the terms of the sequence will be somewhere on the real line, but I know that the limit x is positive, so it will be somewhere here, right? Now because xn converges to x, by definition of convergence, I can find a natural number capital N given any epsilon positive. Of course, if you give me any epsilon positive, I can find a natural number capital N such that after the stage n, that is all the terms after x capital N, they will be inside the epsilon neighborhood of x, that is x minus epsilon comma x plus epsilon, right? So after a certain stage, all the points will be somewhere here. What I will do is I will pick up a particular epsilon positive. We are given that the real number x is positive, right? So if x is positive, then x by 2 will also be positive. X is a real number, so x by 2 is also a positive real number. So if I choose this as the epsilon, it's a positive number, that is x by 2. Then for this epsilon x by 2, I can find a natural number such that after the stage, all the terms of the sequence will be inside x minus epsilon comma x plus epsilon, where epsilon is x by 2 now, right? So this x, epsilon, I can replace it by x by 2, right? And once I do that, what this turns out to be, x minus x by 2 is, if you cross multiply and check, this will turn out to be x by 2, and this will turn out to be how much? 3x by 2, x plus x by 2. So that's 3x by 2, correct? So what this result says is, if xn converges to a positive limit x, then I can find a natural number such that after a certain stage, all the terms of the sequence will be lying here. That means they will be bigger than epsilon by 2 because they are inside this ball. They will be somewhere here, right? So you can see that x by 2 is a number here now, exactly here. This is x by 2, this one. And all the terms of the sequence are greater than x by 2 after a certain stage. And that's what this result says. Okay, then there exists a natural number capital N such that all the terms of the sequence xn will be bigger than x by 2 for all n bigger than or equal to that capital number, right? So geometrically, if you look at it, it's a trivial result, and now we will prove it. Okay, so that is what I have to show. So choose epsilon equal to x by 2, which is a positive number. So for this epsilon positive, since xn converges to the point x, for epsilon equal to x by 2, for this epsilon, there exists a natural number capital N by the definition such that xn belongs to the interval x minus epsilon comma x plus epsilon, this epsilon neighborhood, for all n bigger than or equal to this capital N. This is by definition of convergent sequence, and I'm picking up a particular epsilon, right? So this means I can replace this epsilon by x by 2 now. So xn belongs to x minus x by 2 comma x plus x by 2 for all n bigger than or equal to capital N. This means xn belongs to, this is x by 2 comma 3x by 2 for all n bigger than or equal to capital N. Now this xn lies in this interval. So if x by 2 is here and 3x by 2 is here, the open interval is this open interval which I am talking about, the neighborhood. And the point xn are lying here. That means they are definitely greater than x by 2, right? So this implies xn is greater than x by 2 for all n bigger than or equal to n. So what did we prove? If a sequence xn converges to a positive real number x, then after a certain stage, all the points of the sequence will be greater than the number x by 2, where x is the limit, the positive limit of the sequence. Clear? So this is the proof of the first property. So I can put the conclusion of this property as a remark, and that will say, so from the previous result we come to know that if xn converges to a point x and x is a positive real number, then except for finitely many terms of the sequence, except for finitely many terms, all xn's will be positive. Another way of interpreting the same one. So what it says, if a sequence xn converges to a positive limit x, then after a certain stage, there are finitely many terms now which are excluded. x1, x2, x3 up till x capital N minus 1. Only those are excluded. After that, all the terms are greater than x by 2. And if they are greater than x by 2, because x is positive, 0 will be somewhere here. Because x by 2 is positive. And all the terms are here. Right? So except for a finitely many terms, all the terms of the sequence will be positive. Right? And that's what has been put in this remark. Now another thing to look at here is, what can I deduce when a sequence xn converges to the point x where x is a negative real number, right? So that I will leave as an exercise. I want you all to think over this. Let xn be a sequence of real numbers such that xn converges to the point x and the point x is negative. Okay, the point x which I'm talking about here is negative. Then there exists a natural number n such that xn is less than x by 2 after a certain stage. Okay, this result is analogous to the previous result that I proved, and I want you all to think over this one. So first look at it geometrically, what happens, and then you try to prove it rigorously. Okay, so this I will leave as an exercise, and I expect you all to do this. Moving on to the next one. Before moving on to the next one, you can also talk about the first property which I gave in the exercise together. Okay, so I'll just state that and we will quickly go through it. So that says, let xn be a sequence of real numbers. Let xn be a sequence of real numbers such that xn converges to a point x, and that point x is a non-zero number, right? And that point x is a non-zero number. Then there exists a natural number capital N. Then I can find a natural number capital N such that mod xk is bigger than or equal to mod x by 2 for all k. Instead I can use n only here, so that there is no issue, such that xn is bigger than or equal to mod x by 2 for all n bigger than or equal to this capital. One way to prove this could be, because x is non-zero, you consider this as two cases. X is positive. If x is positive, then the proof for that case will be the first result that I did today, because here also x is positive and other things will remain the same. Okay, and if x is negative, then you will have to prove this exercise, and that will become the second part of this, right? So what I will do is, instead of doing it that way, I will prove it together in another way of doing it, right? So I want you all to try it the other way also, by considering x to be positive and x to be negative separately, but I won't do it that way. I will do it in a different way, right? So let's start now. We are given that xn converges to the point x, right? We are given that xn converges to the point x. So I will choose my epsilon to be this. Choose epsilon to be equal to mod x by 2, which is a positive real number. Since xn converges to the point x, for this epsilon positive, for epsilon equal to mod x by 2, which is a positive real number, by definition I can find a natural number capital N such that xn minus x will be less than this epsilon, which is mod x by 2, for all n bigger than or equal to capital, right? So this is what I have from the convergence. Next, what I will do is, I will consider all the natural numbers which are bigger than or equal to the capital N that we just obtained, the same capital N from here, okay, which we obtained from the convergence of the sequence xn to x. Now if I consider all the natural numbers which are bigger than or equal to that capital N, then for all these natural numbers this condition will work, right? I can call this as something, maybe 1. Condition 1 will work because it works for all numbers which are bigger than or equal to capital N. So for all those numbers I will look at mod x, and to this mod x I will add and subtract xn, where n is bigger than or equal to capital. Okay, so keep this in mind. Now to this I will take this as one term and this is the second term and apply triangle inequality. So this is going to be less than or equal to mod x minus xn plus modulus of xn, right? And this is equal to, I can shuffle these two terms because mod a minus b is same as mod b minus a. So I can shuffle these two terms to get xn minus x, and I have this mod xn here, right? So finally what I have, no, before that, now for all n greater than or equal to capital N, by condition 1, mod xn minus x is strictly less than mod x by 2. So this first term will be strictly less than mod x by 2, and then plus I have mod xn as it is, right? And this is coming by 1. Clear? So finally what I have is mod x is strictly less than mod x by 2 plus modulus of xn, and this works for all n which are bigger than or equal to capital N, right? Then this implies I can just shuffle the term this mod x by 2 that side, and I will have mod x minus mod x by 2 is strictly less than mod xn for all n which are bigger than or equal to capital N. And if I simplify the expression, then this turns out to be mod x by 2, and that is less than mod xn for all n which are bigger than or equal to capital N. And therefore we have what we wanted, mod xn is bigger than mod x by 2 for all n bigger than or equal to capital N. We have a strict inequality here, right? But in the statement we are given that bigger than or equal to. So bigger than or equal to will also work here because one of the conditions is working, that it is greater than mod x by 2, right? So I can write this as mod xn is bigger than or equal to mod x by 2 for all n bigger than or equal to capital. So this is what we wanted, and this property is the combination of the last two properties which I discussed. That is the one which I did first in this lecture and the one which I left as an exercise. All right. So this property is done here. Let's move on to the next one. Next is bounded sequences. When do we say that a sequence is bounded? So let's see bounded sequences and a few examples of bounded sequences. Supposing I have a sequence of real numbers, let xn be a sequence of real numbers. Then this sequence xn is said to be bounded if there exists a real number m positive such that absolute value of all the terms of the sequence is less than this real number for all n belonging to n. Okay, so a sequence xn of real numbers is said to be bounded if all the terms of the sequence, when you take the absolute value, that has to be less than m for every natural number. So geometrically speaking, what does it mean? So if I have a sequence xn, let's say this is 0, in some terms, maybe this side, that side, I don't know, anywhere, then if you look at this expression now, mod x is less than m, I can rewrite this as using one of the properties of absolute values, minus m is less than xn is less than m for all n, right? So what this says, I have a positive real number m here, and its negative will be exactly at a distance m on the left of 0, so more or less here, and all the terms of the sequence xn, they are between these 2 points minus m and m. So x1 is here, x2, x3, x4, x5, somewhere here, x8, x10 could be 0 also, and so on, right? That means the terms of the sequence cannot cross the limits m and minus n on both the sides. So they are within those bounds m and minus n. Okay, so such a sequence is said to be bounded. And if you cannot find such a real number m, then we say that the sequence is bounded. Okay. Otherwise xn is said to be unbounded. So if you are unable to find such a real number m, then we say that xn is unbounded. For example, if you look at the sequences that we had discussed earlier in this chapter, I will pick up few, 2, 3 of them, and we will see whether they are bounded or no. If you consider this xn equal to -1 raised to n for all natural numbers, then this sequence only takes the points -1, 1, -1, 1, -1, 1, and so on, right? So if you take m equal to 1, if you take m is equal to 1, and you take mod of all the terms of the sequence, that will get 1 only everywhere, then mod xn is less than or equal to 1 for all natural numbers n. So we have found a real number m such that mod xn is less than or equal to 1 for each n. Each term is less than or equal to 1, right? Or you can put it this way also. All the terms are between m and minus m because they are here and here. Only 2 points they are taking. So this sequence xn is bounded sequence, right? Next, if you look at the sequence 1 by n, this was one more sequence that we discussed. If you look at this, xn is equal to 1 by n, then all the terms of the sequence are between 0 and 1, right? So 1 half, 1 by 3, 1 by 4, and all are here. So all are less than or equal to 1, right? So here mod xn is less than or equal to 1 for all n. So we have found a real number m positive, that's 1, and therefore this sequence xn is also bounded, right? Now instead of picking up the real number m in both the cases, here you can pick up anything actually greater than 1. Even 5 will work, even 10 will work, even 1.5 is going to work. Okay, and even in the second case, any real number which is greater than 1 is also going to work, because all the terms of the sequence will be less than or equal to that number which is greater than 1. So instead of picking up 1, you can pick up any m that you like, right? Next one is, you look at this, xn is equal to n for all natural numbers n. What are the terms of the sequence? 1, 2, 3, 4, 5, and so on. This keeps on increasing. Is it possible to find, for you to find a bound for these terms? Can you find a real number which will be bigger than all these terms? No, because if you give me any real number, I can find a natural number bigger than that, right? So if suppose this sequence xn is bounded, then all the sequence terms of the sequence will be less than or equal to m, right? So I can say then there exists a real number m positive such that this will happen. Now for each n, xn is positive, so I can write this as xn is less than or equal to m, and that is nothing but for all n, right? For all natural numbers n. So this is for all natural numbers n. But for each n, xn is nothing but n. So this tells me that for every natural number n, m is bigger than that. This means the set of natural numbers is bounded above. That's a contradiction. Right? So that's a contradiction because we know that the set of natural numbers is not bounded above. So our conclusion is that our assumption is false and therefore the sequence xn is unbounded. Okay. What you can do is you can look out for all the other sequences that we saw, all the other examples, and check whether they are bounded or not. Okay, so this I will leave as an exercise to check whether all the remaining sequences are bounded or not. Next, I will start with one convergent sequence and let's see what we can derive from it. So supposing xn is a sequence, let xn be a sequence such that xn converges to a real number x, where x is a real number. So I have a convergent sequence with me which converges to the real number x. Now for given any epsilon positive, I can apply the definition, right? So I will pick up one of the simplest epsilons. You can pick up any epsilon you like and you can work with this. Alright, so I will pick up epsilon equal to, let's say, 1 or 2, anything. So let me pick up 2. You can pick up anything you like provided it is positive. Then for epsilon equal to 2, there exists a natural number such that xn minus x is less than epsilon, which is 2, for all n bigger than or equal to capital N. By applying the definition of convergence of a sequence to this sequence xn, right? So after a certain stage, when I look at terms of the sequence after this capital N, the difference of those terms with x will be less than my given epsilon. I have picked up epsilon equal to 2, right? Now what I will do is I will pick up xn. Supposing I have the terms of the sequence xn. To this I will add and subtract the limit that I have, that is xn minus x. Okay, so xn minus x, I will take this as one term now and this is the second term, and I will apply triangle inequality. So mod a plus b is what I have, and that will be less than or equal to mod a, that is this, plus mod b, that is mod x, right? But after a certain stage, what we know is this xn minus x can be made less than 2 after this capital N. So this term xn minus x, modulus of that is strictly less than 2 plus mod x, and this will happen for all n bigger than or equal to capital N, right? So what we have now, therefore mod xn is less than or equal to 2 plus mod x after a certain stage, right? So if I put it on the number line now, supposing I have the natural number n here, then corresponding to this xn I will have, then I will have xn plus 1, xn plus 2, and so on. Okay, so all these terms are there. What I know is after this x capital N, absolute value of all the terms of the sequence are less than or equal to this number 2 plus epsilon. 2 is a real number and x is also a real number, which is the limit. So 2 plus mod x is again a real number. This belongs to the set of real numbers. And what I know right now, absolute value of all the terms after this x capital N, that is all these terms here, is less than this real number, less than or equal to this real number, right? So the only terms which are left out now are the ones which I am marking in red. They are x1, x2 up till x capital N minus 1, right? I don't know what is happening to these terms, but absolute value of all the terms which I have written in white color here is less than or equal to this number 2 plus mod x, right? Now it is possible that any of these terms here x1, x2 up till x n minus 1, n plus 1, sorry, no, n minus 1 are bigger than this number, they are crossing this number, right? It could happen that a real number 2 plus mod x is somewhere here, maybe here, and it could happen that x1 is here, right? x2 is here. Now don't follow this order here. These are terms I've just written corresponding to these natural numbers. So this might not be the order of the terms of the sequence, right? These I've only written corresponding to each natural number, the terms of the sequence. So the terms of the sequence could be anywhere. So x5 could be here, x3 could be here, x4 could be here, but after x capital N, all of them are this side, right? So x capital N, x capital N plus 1, all of these are this side. So only thing is these terms I don't know whether they are less than or bigger than this real number 2 plus mod x. So what I will do is I will make a set consisting of all these terms x1, x2 up till x capital N minus 1. Okay, x1, x2 up till x capital N minus 1, and along with these I will put this real number that I obtained 2 plus mod x, and I will form this set. This is a finite set because these are n minus 1 terms with me, and this is additional term. So total I have n terms with me, and that's a finite set. What I want now is I want a real number which will be bigger than or equal to all the terms of the sequence. Okay, so what I will do, I will pick up the biggest one in this collection. Because this is a finite set, it is definitely going to have a maximum, right? So choose capital M to be maximum of all these. Okay, choose capital M to be maximum of all these. Then because M is the maximum of this set, M must be bigger than or equal to all these numbers. Therefore xi is less than or equal to M, all these terms, for all I going from 1 till n minus 1, and for terms which are after n, that is x, let's say j, that is less than or equal to 2 plus mod x, and this is less than or equal to capital M now, and this j is n, n plus 1, and so on, all these terms after n. So the first initial terms are less than or equal to M, and after capital N also those terms are less than or equal to M. So from these two statements, what do I have? All the terms of the sequence, I can put absolute value here, because even if it's negative, it will be on this side, left hand side, right? So choose a real number M to be maximum of this. This is positive. So our M definitely cannot be negative because I already have a positive number here with me, right? So even if these terms are negative, this one will be bigger than all the negative terms, and this is going to be strictly positive, right? So finally, what I have is modulus of xn is less than or equal to M for all natural numbers m n. So what did we show? We showed that the sequence xn is bounded. So what did we do here? We started with a convergent sequence, right? We had started with a convergent sequence xn, and we showed that it is bounded here because we found a real number m such that mod xn is less than or equal to m for all natural numbers n, right? So our conclusion is that if I take any convergent sequence of real numbers, that is going to be bounded. And this is the next property, which I will put it as a theorem now. Every convergent sequence of real numbers is bounded. So no matter which convergent sequence you take in R, that sequence will definitely be bounded. Okay, a very important result, and at many places we will be making use of this result. All right. So this finishes this lecture. In the next lecture, what we will do is, we've given any two sequences, we will generate more sequences from the given sequences. All right, so the next lecture is going to be an interesting one. So I will stop with this. And these are my references. Thank you.